So and at the end of the day, our model performed what we find to be really, really well, really high, 0.92, so it's very high. Okay. Oh, and I also want to mention that the way we, the reason that there's a standard deviation in this system, in our results, is that because the way we evaluated our system is we had 10 subjects. Our models trained on 9 and then evaluated on 1 held out. And we did that 10 times. So we rotated through all the different subjects to show that no matter who you're training on, this model generalizes over all the different kinds of people you have in your experiment. So that's why there's a variance between each evaluation. Okay, so that was us evaluating the overall conversation. Was it happy or sad? But it would be really neat if we could actually figure out every 5 seconds, really, was the individual happy, sad, or neutral. And so that was the next set of evaluations, or the next set of modeling that we went out and did. So using the same 10, subjects and the stories that they had narrated, we scored every 5-second interval to get a label as happy, sad, or neutral. This time 3 classes. And the reason we did 3 classes will show you why. When we went and looked at what is happening in happy stories, within the happy stories, or the happy narratives, we found that there were many different what we call moments in a given story. So we evaluated each 5-second interval according to there is a sort of like an emotion wheel. You can think of like a color wheel, but there's one for emotions. And so anything from sad, loathing, angry, all the way to admiration and happy. So what we noticed within a happy story is that it's not just filled with these positive moments, but there's also negative moments as well as neutral moments. So you can imagine, think of any standard story or like a classic Disney story. There's always the high point, low point, high point again, and so there's a lot of things happening within these stories, which are something like 2 minutes long, which was really, really interesting. So we said, oh, okay, like we really should be trying to capture what's happening at lower level, at the lower story level. And so same thing when we looked at sad stories. It's not just filled with these negative moments. There's neutral moments and even positive moments within sad stories. So that really sort of found really interesting. We really should be trying to capture these 3 buckets of them into 3 different moments: negative moments, neutral moments, and positive moments. And so what we wanted to do was again model 5-second intervals, and we thought we'd try out a more sort of in fashion or I guess in fashion modeling paradigm, which are neural networks. And they're powerful because they can, there's sort of a black box in the sense that there's all these different computations and mathematical transformations happening within. So unlike the previous model that we used, this black box of it, or this neural network model, is able to, or will try to model all kinds of interactions between the different features. So you can imagine that if someone is speaking very quickly and with a really high pitch, those 2 together, like multiplied, are super predictive of that they're expressing a happy moment. And so you want to capture those kind of complex interactions between these different features, and neural networks are able to do that. But still, they're kind of a mystery. They're black box, so proceed with caution. And so there are many different ways to optimize this kind of model, and there's a lot of work that's being done in this domain. If you've heard about, if anyone's invested in like GPU companies like NVIDIA or AMD.
Oh yeah, you made a lot of money for those of you who invested in GPUs.
Because not just Bitcoin being GPUs, but these models that Google's buying like thousands of GPUs at once, and they have huge computational warehouses.
It's actually hard to buy a GPU these days because people are, okay,
Both for
Those of us who want to innocently use them for just gaming can't even find them anymore, right? Like, because people are using them for computation.
yeah, all kinds of computation, bitcoins on these neural network stuff. So yeah, so we wanted to, because there's so many different, what they call hyperparameters or parameters of the system that you need to optimize for, that you not only model or run a computation for a single model, but you have to run hundreds and hundreds, if not thousands and thousands of models trying to figure out what the optimal size is, what the optimal shape is. And so we ended up exploring different hyperparameters of this network. You could have a network that had no layers, 1 layer, or 2 layers, and it can have the number of nodes or the number of logistic regression, like that single model that we had been modeling. You can have many, 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 many of those together.
Working together.
And
That's
so-
actually so that you know basically what a neural network is. It's just a bunch of those logistic regressions, daisy chains together. So that the line band algorithms.
Or even linear regressions. I mean, you could have whatever mathematical transform, not whatever, but inside these systems. And so we also wanted to, so we ended up doing that, and we generated a heat map to show, okay, if you're going to explore this space of several layers, or you can have a neural network with 1 layer or 2 layers, and different nodes within each layer. There's some optimum number of nodes within each layer that you can have in order to have a classifier that performs really well, or a model that performs really well. And so what you want to do is find these peaks or these hot points, and that's the optimum size of your network, which we ended up finding was a network where the first layer had 6 nodes and the second had 3. But there's even more optimization that you can do with these kind of networks, and it's really up to your imagination.
You might want to just, for the sake of time, maybe you should just jump to the results.
Oh, okay, sure. So you can compare these networks, pump features in the way you want them, many, many different things you can do. What was really cool is that depending on how you introduce these features, so positive, negative sentiment, which is a more abstract feature relative to, say, the energy in your voice, or energy in your voice tends to be put up higher than that. But that's more sort of for the computer science interest.
Tuka, is one circle like one model, like one of the logistic models?
Yes, exactly.
You got it.
Yeah.
You got it.
So that was our initial model, and then you can have all these working together, and you can even pipe these features in different layers.
The reason they're so flexible, by the way, intuitively, is that imagine every time I put you through one of those logistic regressions, imagine I get to bend a line. So I give you first a string, and I say every time I put you through one of those, you get to bend it. So you're going to, after several bends, right, you're going to be able to create a line that looks like whatever you want. And that's why the neural networks are powerful. Because they can map a given x, whatever it is, to a given y, basically perfectly. Because they can just keep bending the line until they get exactly what they want. Does that make sense? Yeah. So a linear regression is a single line. A logistic regression is a line with one bend. A neural network is a line with you keep bending and bending and bending and bending and bending. And you can get the line to look however you want. Does that intuitively make sense? Yeah.
So in like the second box with the 3 different kinds of models, when you say you added those variables, what is it? Does that mean you've bended a line for those specific variables?
Here's the way to think about it. So there's 5 of them. There's 6 in the bottom one there, right? So imagine I have some string, and I call 6 people up here, and I say to each of you bend the string the way you want. But we're going to work together to bend the string so that when we tie it together at the end, it looks like some picture, or it looks like a sentence. Let's say we want to spell my first name. So I give each of you in the 6 a piece of string, and I say, we each have to bend it in a way so that when we tie it together at the end, we're going to be able to spell the name Mohammad. We can only do one bend on these strings. You also know that you're going to pass it to 3 more people in this room who are going to get to bend it one more time. And then you're going to get to pass it to a final person who can bend it one last time. Okay? So those 6, 7, 8, 9, 10 people are all working together to bend this so they can spell this word Mohammad. Does that make sense?
Mm-hmm.
Right? Yeah.
And also, I don't want to go down a rabbit hole or anything, but So what determines which features are included in which layer? Like, like which one, is it because they're more statistically likely of
Yeah.
occurring to be correct or something?
You can go ahead and, yeah.
So, the way we did it was we ended up introducing them, like we tried all these different configurations and just evaluated and saw, okay, this is the optimum placement of the features in the network. But to reverse engineer and say, is it because it's more statistically, like, can I plot that bar chart for you that I did in a previous slide? No, actually that's the weakness of these new networks, is they don't allow you to, they don't allow, you know, me to give you a plot and say, this is exactly the impact of each feature, and have a nice bar chart for you.
Yeah.
So at the end, you can't get coefficients for each
Exactly.
of the
I
variables?
mean, there are coefficients, but it's hard to piece like how they tie back to these features.
Okay.
And it's because, you know, they're all sort of, when you have them all working together in a multi-layer fashion like this, you know, even like top mathematicians are actually trying, like across the world, to reverse engineer how you can interpret the coefficients of these models. And nobody's cracked it yet. It's just a mystery, you know, how they work. Everybody knows they work well, right? But
They trust it.
it's, it's a trust thing.
Exactly.
And actually, for those of you, I mean, those of you who have Siri on your phone, the reason Siri does well is actually because of these neural networks. It takes the raw audio and it bends and bends and bends, and then it creates a transcription at the end, like the string I told you, right?
Yeah.
Oh, this is the word Mohammad, this is the word cat, this is the word dog, right? You know, so.
So yeah, so that's what we were doing, evaluating. And we also evaluated performance. In this case, we did accuracy because we have 3 classes that we're working with. There are metrics that are like AUC, but they become, I mean, you can still.
Volume understand.
Yeah. So, and we could do pretty well with this additional optimizations. I think what you should take away from this. Oh yeah, so let me also show you a video, and that's probably will be the end of this overview of our, you know, our work.
Oh, you want to turn the volume up? Restart. So this is actually it running live on a person telling a story, so you can see what the end result was. Oh.
There you go, so I don't know. There you go, part of the audio.
Maybe try plugging this back?
It's okay, I'll just.
Oh, there we go. We can do it.
First day. So I was just ready, and then